to start the recording and say, make sure everybody can hear me. I know at least one person can. There's some thumbs. Can one of the Zoomers please say hello so I can test the audio on here? Please?
Hello, Lisa. Can
There
you hear
you
me?
go. Thank you. Yes, I
Great.
can see the
Yeah.
green move on the recorder thingy. That's what I was looking for. So it's all good. All right. So, yes, welcome to my office as opposed to our classroom. I heard yesterday that there is now a sign in there saying that there is no more laptop input and no one knows when it's going to be fixed. So, we're here today making this work. We will be here on Thursday as well on Zoom. That one was planned though. Nathan, do you have any updates at all by chance? Can't hear you. I saw that you unmuted yourself though.
How about now? Are we good?
Yep, now I can hear you.
Okay. So yeah, I'm still teaching in that room, and we were having. I think it was the reason why that sign got put up. We were doing group presentations, and people just could not connect at all. Or like we had to hold. It was not fun. So I'm hoping something happens soon, but because we have more presentations and whatever. But the way things go, it's always weeks and months sometimes.
Okay, so a nice optimistic update. Thank you. Yeah. Well, that's maybe the one nice thing about the pandemic is that we all just learn to adapt and try to make it work. And if the classroom doesn't work properly, then we'll just do this. So I hope your presentations can find a way to keep going because that would be quite, I mean, it's nerve-wracking giving a presentation anyway, but to have tech in the middle of it break is even worse. So,
Yeah, I think to bypass it and different connection, but
hmm? So be it.
for a point.
Say that again.
Oh, I'm driving, so you
Oh.
may be hearing the tractor trailers next to me.
Okay, so maybe don't connect to class while you're driving. That does not sound like a safe
Oh,
thing
I
to
have
do.
Bluetooth.
Okay.
So
It,
we're good.
oh, attention doesn't care about Bluetooth though. Divided attention is the problem. So please don't wreck yourself. I forgive you for being late. It's fine.
Okay.
Or not being here. I forgive you. It's fine. All right. So we don't have anything to talk about with respect to assignments today because you got the end of last week off since I was out of town. I did put up your next formative assessment though, and that will be due in about a week, next Monday. And towards the end of this week, I hope to have your next assignment up, assignment 3, which will be over models with linear and quadratic time slopes. So continuing on with the theme. And I hope that we will be able to finish quadratic today, Thursday for sure. That way you will have all of the tools that you need to complete the homework once I put it up. So any logistics questions, anything that I'm forgetting about that you want to remind me? Anything like that? Try and get us situated. Quiet group today. Okay. Then let me share screen with y'all so that you can see what I see.
Sorry, a quick question.
Yeah, hit me.
Can we take the formative assessment now, or do we have to wait until the end of this week or something?
It should be available now. Did I not hit publish on
Yeah,
it?
yeah, but the content.
Oh, the content. I would say after today you should be in good shape, or if you've done the reading for this unit, then we're asking about random linear models as well as how to get predictions out of a quadratic model. So that's one thing we started talking about last time, and then after today you should be able to answer all the questions.
Great. Thank you.
Thank you. So I am on, let's see here, page 7 of the handout that we were working on last time, handout example 6A. And let's see, yeah, page 7, I said that part. Are we ready to dive back into this stuff? As ready as we're going to be, at least? Yeah, ready is a relative term, isn't it? So we were, just to reorient you to the example data that we have here, these are 6 occasions of measurement. The outcome is response time, so lower scores are better, meaning that they're doing the task faster. And the object of this study was to examine individual differences in the effects of practice on this test and to see essentially what part of the variability is in response time is attributable to individual differences in learning as opposed to other things. So we did the random linear time model last week, but I wanted to start here again so that it can be a comparison against the quadratic models that we have not yet seen an example of. So on model 2B here, random linear time model, this one has 2 different kinds of individual differences in it. We have individual differences in the intercept, which as always is going to be the expected outcome from the model at time 0. In this model, time is centered such that the first occasion, session 1, equals time 0. So it's session minus 1 is how that variable was created. So we have individual differences in the intercept at time 0, and then we also have individual differences in a linear rate of change, so allowing differences in people's improvement in response time as a function of increasing practice on this task. So the predictor that is being treated as a quantitative variable, time right here, shows up in 2 different places in all 3 of the programs, as a fixed effect in the model line, as a random effect or random slope in the random line. Same thing in Stata, we had fixed effect over here next to the outcome, as well as the random effect for time after person ID, which is our level 2 nesting variable. And in R, today we are using Elmer for right now. And so we have time here as a fixed effect, there we go, and time as a random slope as well. And we went through the output before, talking about the G matrix, so reviewing vocabulary. What kind of variance lives in the G matrix? And I am watching the chat too, if you feel like typing or talking, your choice. BP, yes. Synonyms. Level 2, I take it, yes. What else you got?
Random
Random,
variance.
yes. 2 hands on the wheel, Nathan. I'm just kidding you. Yes, random, level 2, between person, inter-individual. And this is where the cross-sectional part gets a little bit fuzzy. So that was one that I had added initially to describe between person intercept differences. Mean differences represent cross-sectional variation that would have been there had you only measured people once. However, I would hesitate to call slope variation cross-sectional. The way that you can think about it is that the slope for change over time, so the fixed effect that goes with time as a predictor, that slope represents a within-person effect. It is quite literally the difference between where you were at time 0 relative to where you end up at time 6, drawing a straight line, or session 6, time 5, drawing a straight line through those points. So it is a within-person fixed effect that we are allowing individual differences that are between person. So it's a random slope. The idea is that it is level 2 between person variance in a level 1 within person slope. And yes, that will be a homework question at some point, I can guarantee it. So I would say intercept at level 2 is cross-sectional differences because they're related to either the mean over time or the mean at time 0, whereas slope differences I would not call cross-sectional anymore. It's between person differences in a within person slope for change over time. So we have our level 2 G matrix. That means what's left over in R. So more vocabulary drill here. How would I describe the contents of the R matrix? This empty looking thing right here.
Time varying.
Yep, time varying, that's one. Level, what number? Level 1? Yep. And the opposite of between? Within person, yep. Yep, so these, the the e's, essentially. What we're seeing in the R matrix is the variability of the e's. So the deviations of each individual's actual outcome relative to the growth curve that is predicted for them. At this point in the model, though, it's not a curve, it's a line. So E is, why are you off your line today? Why doesn't that line fit perfectly? And the only way that we could potentially explain E variance is with predictors that also differ over time. So what happened today as opposed to time constant things. So yes, level 1, residual variance. And the empty space in this matrix is illustrating the idea that we are assuming in this model that the level 1 E's have constant variance across time and that they have no covariance. So all of the reasons why occasions from the same person are related is because of what's in G at level 2 is because of between person intercept and time slope differences. That's what this model is saying. Once you control for people's individual differences in where they start and how they change, then the E's are supposed to be independent. That is a testable assumption, which we will investigate a couple models from now. So the V matrix then is the put back together again marginal predicted covariance matrix. It is called sigma in SEM land, but this is what the model says the pattern of variance and covariance should look like over time. And where that pattern came from is given in these two equations right here. So the top one tells you what the predicted variance is at each occasion, and the bottom one tells you what the predicted covariance would be between any two pairs of occasions. And the key idea here is heterogeneity. Once we add a random linear time slope, we are predicting heterogeneity of variance and covariance over time, not homogeneity. So we're predicting that variance changes quadratically as a function of time squared. All right, so then we have our fixed effects in this model. So they were right here. Let me see if I can make this a little bit bigger. So 1900 milliseconds is where people are predicted to start at time 0, session 1, on average. And this fixed linear time slope is significantly negative. And I can say that because I'm staring at the p-value that goes with the test of that wall test for the coefficient. So the estimate divided by the standard error gives us our t. With this denominator degrees of freedom, then is where the p-value comes from. So on average, people are improving at a rate of 52 milliseconds a session. We did a likelihood ratio test, or log likelihood difference, you can say it either way, to test whether or not the random slope variance and its covariance with the intercept help the model relative to only having a fixed linear time slope, and that difference in the -2 log likelihood was 42 on 2 degrees of freedom, definitely a significant improvement. So there is evidence that people do need their own slopes for change over time. Then we do confidence intervals? I think we did this part, right? We did that. So you got a chance to practice that in your last homework. You are likely to get to practice it again. So any parameter that has both a fixed part and a random part is eligible to have a random effects confidence interval. Any parameter that only has a fixed part would not have an interval around it. The interval would be, there would be no space around it. The fixed is the center. Having the random variance around it is what allows the interval. So we can then describe the size of the variability given by the random effect variances in terms of the original outcome. So this confidence interval is telling us that on average, it takes people about 1900 milliseconds to do this task the first time they try. The model predicts that range across participants to be somewhere between 913 milliseconds up to about 3 seconds. So quite a bit of variability in the predicted outcome at time 0. Likewise, on average, people are declining by 52 milliseconds a session, whereas the individual variability around that fixed linear time slope implies individual slopes somewhere between -145 milliseconds a session all the way up to +42 milliseconds. So some people are actually predicted to increase in response time due to practice, not improve. So then we have quadratics. So do you remember talking about quadratics last time? Anybody? I'm going to try and phrase my questions as thumbs up or thumbs down. If you remember talking about quadratic slopes last time, thumbs up me. Thank you. That sounded kind of obscene. I didn't mean it that way. Send me a thumbs up? That might be better. Yes, you remember that. And what's the magical rule? To interpret it correctly, what do you need to do?
Divide by 2,
Other way around. So close.
or multiply by 2.
Multiply by 2. That's it. Twice the quadratic gives you the rate of acceleration or deceleration of the linear slope. Twice. So we take the quadratic coefficient, multiply it by 2, and then we can talk about how it changes the linear slope as time goes on.
Lisa, I wanted to ask, is that because when you take the derivative of a squared quadratic, that 2 comes down in front and multiplies whatever comes after by 2?
Yes, that is exactly
Okay.
why. Yep. So in these models, if you picture like a U-shaped trajectory, the first derivative of that function is the linear time slope. The second derivative then is the quadratic time slope times 2, because when you take the second derivative, the 2 up in the exponent of time squared has to come down in front. That's why. You can also think of it as a consequence of time squared being an interaction term that would normally have 2 roles to play with respect to how it modifies its constituent main effects. But because time is only one main effect, it has to operate on it twice. That's the other way that I tried to explain it. So how we come up with a predicted intercept at any occasion or a predicted linear slope at any occasion is given to the right of the model equation here. So if we start with model 3a on page 9 of example 6a, we have fixed quadratic random linear. So the change to the model then, we had beta 0 for the intercept before, we had beta 1 for the linear time slope, now we're picking up beta 2 for the quadratic time slope. Because we have 3 betas in the level 1 equation, that means we need to have 3 separate level 2 equations, one for each of them. In SEM notation, this would mean that we've added a third latent variable circle, one for each beta. Same idea. So the intercept and the linear time slope have both a fixed part and a random part indicated by the gamma terms and the u terms, respectively. The quadratic time slope does not yet have a random part. So this model is allowing the linear slope to either speed up or slow down on average. It is not yet allowing individual differences in the extent to which people speed up or slow down. So this is the model equation then. I have the words predicted intercept at any occasion, and that you can also think of as conditional mean, expected value, model predicted outcome, intercept. All of those convey the idea of, at a particular occasion, what does the model say the mean should be given the fixed effects? So I use the term intercept here to make the point that, yes, our intercept is locked into what time 0 is. If you wanted to know what was the intercept going to be, say, at time 4, you don't need to re-estimate the model with a differing centering point. The model will tell you what the intercept would have been for any value of time. We just have to substitute it into the equation with the fixed effects. So to get the predicted intercept at any occasion, it's a function of gamma 0, 0, which is what would the intercept be at time 0, and then the linear effect of time and the quadratic effect of time then modify that predicted intercept. So I will show you how we can write programming statements, estimate in SAS, LinCom and Stata, or margins will also work for this. And in R, I'm using Contest 1D to write predicted outcomes for any value of time. So it could be any value of time that we've observed or any value of time that we haven't, because this is a continuous function that implies some predicted value for any possible level of time. Okay, with me so far? That was supposed to be a thumb question. Thumbs up if you're with me. Poop emoji if you're not, maybe. Let's go with that. Or angry face emoji, something. A heart. Oh, thank you. Does that mean like you're really with me? Like that's an endorsement? I like the heart. That's nice. Good. Okay, so now the tricky one. To figure out what the linear time slope would be for any value of time, the model tells us this. So the rules for figuring out a simple slope given an interaction term are not any different. We would go into the model fixed effects, find all of the terms that have time in them, bring them down, and factor out time. So if I go into gamma 1O times time plus gamma 2O times time squared, bring just that part down, and factor out time, what's left is what's here on the right side of the equals. So the term that is used, and this is a physics reference or calculus, instantaneous. So the idea that you have this U-shaped trajectory, it's the slope at a point. It would be the slope of a line that is tangent to the curve at an exact point. That's what we're trying to figure out here with the instantaneous linear time slope at any occasion. So this little equation here starts with gamma 1O because that's what the model says it would be if time were 0. If time were 0, the rest of this would drop and you'd just be stuck with the linear time slope as the linear at time 0 specifically. We instead, though, for a different occasion, would need to add the fixed quadratic multiplied by 2 and then the value of time that we want that predicted slope for. So the key then to write these estimate statements correctly is to remember to take the value of time that you want the slope for and multiply it by 2, because the 2 needs to get into this prediction. Question, it's basically a derivative of time to estimate change at a specific time point, right? Yes. This is, what would the first derivative be at a different point besides time 0? This is how you figure that out. Yes, so those of you who've seen and remember derivatives, let's put it that way. I used to be really good at derivatives, but that was like 25 years ago and that shit's gone. Okay, that's not happening for me anymore. So if you're familiar with that, yes, that's what I'm talking about. If you're not, 2 times the quadratic is what you need to remember. That's the key to getting this right. Okay, questions? No. Shall we see it in action? Why not? So time squared is the new predictor that we are introducing into the model as a fixed effect only to start with. So I can do that in each program without having to make time squared as a new variable. You could make it as a new variable, you don't have to. So I have time star time in SAS, is how you make interaction terms on the fly. In SAS, I am also writing estimate statements. If I can squish this, yes I can. So the first 6 estimate statements are giving me the expected intercept for any value of time, where the first one is the one that's given by the model directly. So remember, in these types of statements, when you see a word, what it's actually referring to is the fixed effect that that term is going to have after the model is estimated. So intercept means, what is gamma 0, 0 going to be? Give me one of those. I'd like one of them, please. So time then is, what is the fixed linear time slope going to be? And if I want it for time 0, I don't need any of those. And time at 0 times time at 0 is still 0. So this is the one that's going to be given to you by the model parameters already. I include it here for completeness and so that you can see the pattern. So to get the predicted intercept at any other occasion, it is an intercept at a minimum plus what value of time you want the prediction for. So if I'm talking about session 2, that's time 1. And so I fill in a 1 here, and I fill in a 1 here because 1 times 1 is 1. So it's the value of time as we go through the statements, and then time squared is the number that shows up at the end of the quadratic term. And those 3 pieces are enough to give you what the model says the predicted outcome would be on average at any occasion, including those in between potentially. So that part is not new. That is not any different than how you learned how to generate predicted outcomes from any kind of linear regression model, because we're just using the fixed effects. We're just talking about what's happening on average for the average trajectory. Okay, then the trickier part. So rather than asking what would the predicted outcome, the value of the y-axis be at each occasion, now I'm asking what would the linear time slope, what would the first derivative be at any particular occasion? So the intercept is no longer relevant. What we need instead is just the contribution of the linear time slope. So note that that's the same all the way down because we start with what it would be at time 0, and then we modify it based on what occasion we want the linear time slope for. And it is that occasion times 2. So this would have been occasion 1. 1 times 2 is 2. This would have been occasion 2. 2 times 2 is 4, and so on. So this is the tricky part to get right. If you're predicting an intercept, what goes behind time squared is time squared. If you're predicting a linear slope, what goes behind time squared is time multiplied by 2 instead. All right, how are we doing? Thumbs, okay. So the idea is that you're not locked into time 0. You have to set something as time 0 to estimate the model, but you can ask what the model would predict at any other occasion for both the intercept, expected value, and for the linear time slope. Now, do I need to go through this process and talk about what the quadratic slope would be at time 1, at time 2, at time 3? Do I need to do that or no? Do I need to write out these types of programming slopes to figure out what the quadratic fixed slope of time would be at any occasion or not, is my question. Oh, no one's feeling brave. No for now.
Is the
yeah.
answer for no? Is the answer no because that's still like constant in a sense?
Yep, that's exactly right. The answer is no, because the quadratic slope is constant. So if I go back up into the equation here, I need to find all of the terms that have time squared in them. This is it, just the one. So the quadratic slope for time is the highest order term on the fixed side. That means it is unconditional. Another way of saying it is that the linear slope slows down constantly. The second derivative is constant. However you want to say it. Your instincts are right, though. So we don't need to do that. We would need to do that if I were going to fit a cubic model, but I'm not going to do that to you. I don't like cubic. All right, moving along then in terms of the code, it is hashtag or pound sign in Stata to make an interaction term on the fly in the fixed effects. And I am using lincom instead of margins to keep the code across programs as comparable as possible. So lincom then shows the linear combination that is needed to create a predicted intercept more explicitly. Same thing with the linear time slopes. It's whatever the linear time slope would be plus twice the time occasion you want the linear time slope for. And in R, you could have used prediction or, the analog to the margins package, or probably a bunch of other ways to do it. Again, for comparability and transparency, I'm using contest 1D, which is within the Elmer test package. And as usual, all of the packages that my examples need are going to be at the start of the syntax file. You don't have to go track those down. And
Lisa,
so,
can I ask a quick question? So let's say that, so you can either have something that slows down in a constant way, but if it speeds up, but it's not like, let's say it's the opposite. Would you still use a quadratic expression to express that, or would you use something else?
So you're right that these models imply a constant rate of speeding up or slowing down. I didn't follow the rest of the question though about when I would use it.
So like, do you have to do something different if like instead of it speeding up, it slows down?
No,
but
you do
it's
not.
Still okay.
Nope, the signs of the coefficients are going to tell you what's up. So the quadratic is going to take the linear time slope and do one of four things. Make it more positive, more negative, or less negative. And it's just, the combination of the signs of the linear with the sign of the quadratic is which dictates the quadrant that you're in with that. If you expected it to slow down but then speed back up again, this model can't do that. That's what a cubic would be, or a different approach that would have an additional multiple changes in the slope to it would be what you'd need if it's going to slow down and then speed up, or vice versa. This model assumes that if it slows down, that it's going to keep slowing down. The U is going to turn over, though. It'll either come back up or come back down, depending on which direction that you're in. We've got some pictures of that coming up here in just a sec. Okay, does that help?
Yeah, thank you.
Sure. Okay, so these numbers in here, inside the R code, folks, these are multipliers. And the one that's in every entry in the first column here corresponds to the fixed intercept, because if you're predicting any kind of expected outcome, you need a fixed intercept at a minimum. The second column is the values of time, and the third column is the values of time squared. And then down here, when we're predicting the linear slopes at a given occasion instead, we don't need a fixed intercept to do that. We need at least one of the linear time slopes, and then we need twice the value of time that the linear slope is for. So I always put in my R code a 1 to represent the fixed intercept, to remind me that when I'm writing out these statements, that's what comes first. In R, you can make a squared term with this combination. It's a capital I, and then in parentheses time, and then I call that a caret. Does that sound right? It's the thing above the 6 that means squared in programming languages with the 2. So that gives you the time by time effect. It doesn't work in the random part necessarily, I've found, but it does work in the fixed part. Okay, any questions on code or logic that the code is trying to execute? All right, let's see what happened. So the model for the variance has, I should say, the exact same structure because we haven't changed it. So on the variance side, we still have the same 4 parameters: random intercept variance, random linear time slope variance, the covariance of those 2 random effects, and the residual variance that's assumed constant. So those are the 4. So the shape of the V matrix that this model implies is going to be similar, although the estimates are a little bit different because the fixed effects then have defined the average trajectory differently. So we would focus on those predominantly. So here are the 3 fixed effects. So the intercept used to be about 1900 milliseconds. It is now 1946 milliseconds. Why did it change, is my first question. Does it mean something different in this model relative to the previous model? It does not. The intercept is the expected outcome when the predictors are 0. We have not added any new predictors that would have a different 0 point. So this is still the expected outcome at time 0. The reason that it changed is because of the difference in what is expected. Previously, the 1899 was expected from a straight line at time 0, and this is expected from a bendy line. So the prediction has changed, but the interpretation of what the fixed intercept is supposed to mean has not. Still the expected outcome at time 0. Likewise, my linear time slope. So could I say for every additional session of practice, people improve at a rate of 120 milliseconds a session? Can I say that? I cannot. That sentence is incomplete. What do I need to tack onto it somewhere to make it correct? So the rate of improvement is 120 milliseconds a session, ...
Squared?
Not yet.
Okay.
Not yet. Hold on to that. Yeah, at time 0 is where I was going with this. So previously, the rate of change from the linear time slope was like minus 52 milliseconds. It has changed a lot because it means something different. In a linear model, the linear time slope is constant, which is another way of saying it's the average rate of change. Here, this is the rate of change at time 0 specifically. So it's at the beginning. This is going to be a downward U. People are improving, going down, and it's going to be leveling off at some point. So it's minus 120 at time 0 at the beginning. It would be a different number if time 0 were in the middle of the data, the end of the data, or any other place. So this coefficient takes on a different interpretation, a necessarily different value, unless you have mean-centered time. And it happens to be significant, which means we would typically keep it. But even if it were non-significant, we keep it. Because in order for the quadratic fixed slope that's coming to be interpreted properly as quadratic beyond linear, linear still has to be in the model. So even if the instantaneous linear slope at time 0 is not significant, we keep it for interpretational purposes. So now the new one, the quadratic coefficient. So I have a negative linear slope at the beginning of the study paired with a positive quadratic. So which of my 4 patterns is this? More positive, less positive, more negative, or less negative? Negative linear paired with positive quadratic. Yeah, this is a less negative. So people are improving in response time, yes, but they're improving less as time goes on. Practice helps less the more practice you have. So this is a fairly predictable and classic result in the learning literature, particularly for speeded tasks. You get a lot of improvement initially, less improvement as time goes on. Now to talk about this, like to put this 13 in a sentence, what do I need to do to it? The magic trick? This is sort of a finger question. I don't know if there's an emoji for it. Times 2, yes. Multiply it by 2. So the way that I would say this is at the beginning, there is a negative slope of 120 milliseconds a session. For every additional session of practice, that rate of improvement becomes, and I would say it's something like less negative, or the rate of improvement slows down by 27-ish milliseconds, whatever this is multiplied by 2. So the slope at time 1 would be minus 120 plus twice the quadratic. And indeed, we can see those predictions in the rest of the output here when we get to the linear slopes. So minus 120 is the model predicted linear slope at time 0 as given by the fixed linear slope directly. Then to see what it would be at the next occasion, it's twice the quadratic slope coefficient. So the difference between these is twice the quadratic. The next difference is twice the quadratic, and so on. So it looks like at the first occasion they're improving significantly. At the second occasion they're still improving significantly. The rate of improvement starts slowing down, and by the time we get to session 5, it's not different than 0. It flips between session 5 and 6, so the U is starting to come back up again, and the slope that is predicted by the model at the last occasion is actually positive. So if I were to use these results to try to plan how much practice people need, how many sessions do you think I should give people? Yeah, 4 to 5, I would say. After that, it doesn't look like it's helping anymore. So you can use these sorts of results to try to gain efficiency in terms of when people are going to shut off their change, so to speak. But this assumes that everybody is decelerating to the same extent, which may not be the case. So this is an average result. So then what the model actually predicts from the combination of the fixed intercept, the fixed linear time slope, and the fixed effect of time squared are these right here, and so then you could throw these into a plot to show what the model says should happen to response time. So you can see that the difference between these is gradually decreasing and would eventually come back up if you follow time into the future. All right. Okay, how are we doing? Any questions or things you want me to repeat or say differently? No? Okay. So in terms of effect size, how can I think about effect size from this new fixed quadratic slope? One thing I could do is take the t-test statistic that goes with it and convert it into like a partial r, something like that. If I wanted to talk about variance accounted for, how many different kinds of variance are in my model right now? We'll go back up to the covariance parameter estimates. 4 parameters, but one of them is a covariance, and so we usually don't talk about that in terms of an R-square. But I've got 3 left. I've got intercept variance, I've got random linear slope variance, and I've got residual variance. Which of those 3 should time squared as a fixed effect have reduced? Got 1 vote for level 1. Level 1 is correct. The rationale is that level 1 variance is E variance is why are you off your line today? Well, because you gave me a straight line and I need a bendy line instead. More generally, time squared is a level 1 time varying within person predictor. So any effect that it has should at a minimum reduce the level 1 residual variance. So any predictor at the same level accounts for variance at that corresponding level. Time is within persons, should explain within person residual variance. Now the tricky part is how to think about it, because we have this pile of 3 different sources of variance already. So the variance has already been carved up in this way. We're trying to attack what's left over at level 1. So the way that I would think about effect size, we've got the comparison models here, is 6% of what was not already accounted for by the model, we've now explained. So it's not of the original variance, it's not of the level 1 variance, it's at this point in the model, we have another 6% due to time squared. So that can be a little bit tricky to explain as long as you try to say, in your narrative, what is happening at each point, that can help your reader follow, as well as tables of estimates too. It can be more convenient in these models to load up all of your fixed effects first before you add random slopes so that you can talk about their joint effect size so that, the trajectory explained this much of the residual variance, for instance. That can also work. But I'm going fixed, then random, fixed, then random in this particular example. So 6% of the residual variance that remained after linear time, after controlling for individual differences in the effect of linear time. That's what we have here. And the other ones actually went up a little bit, which is not unexpected. Anytime you explain residual and not the others, they're going to go up. Okay. Ready to see random quadratic? Why not, right?
Lisa, can I
Yeah,
ask you something?
please.
So in this case, in the last model, we can calculate the effect size for predictors. In this case, the 2 slopes for time, linear and quadratic, and we can calculate this kind of pseudo R square, but the interpretation is different. right? Because the linear slopes will be useful to account for variance, but this pseudo R square, what it's trying to do is represent the residual variance remaining after
Mhm.
including time predictors, right?
Yes, yeah,
Okay.
so the order was we added a fixed effective linear time to a model that had two piles of variance, just intercept and residual. And then we could talk about how much of residual the linear fixed effective time accounted for. But then we went off in a different direction and added a random linear effective time, which then turns it into a three pile model. And so relative to the three piles, we have another 6% of the residual explained by fixed quadratic time. And it's the another part is the thing. It's like of what we didn't already allocate, now we've picked up another 6%. There are other options for pseudo R squared that are not based on an explicit comparison model. There is an article on your reading list, Wrights and Sturba. I think there's probably 2 or 3 of those papers that are coming up that focus on computation of R squared and how you can do it out of one model as opposed to comparisons of models. But even then, it's tricky because anytime that you reallocate variance, it's hard to compare back. Like if I have a 2 variance pile model versus a 3 pile model, like those are kind of on different scales in the sense of what the piles represent and the conditionality of what's at time 0 versus not. So that's why I think you just have to say it's like another 6% of the residual. That's the key idea.
So yeah, just to be sure about this, that 6.2%, that's the variance explained adding the fixed quadratic linear time slope compared to just the linear
Yes.
time slope.
Yeah, the fixed quadratic time slope above and beyond random linear.
Okay,
Yep.
yeah, thank you.
Mm-hmm. Yep. All right, anything else before we look at random quadratic? All right then. So we're going to play the Where's Waldo of statistics. Do you know this game where there's like a picture and it's usually a very crowded picture and you have to find a character whose name is Waldo and he's in a red and white striped shirt? Well, I like to play a version of this that I call Where's Waldo equation style or code style. So find the one thing in this model equation that turns this into a random quadratic model. What's the new part? At the top of the screen here on page 12. Yeah, U2, not just a great rock band, also an individual quadratic. So yeah, now the fixed quadratic time has a random part to go with it. So the idea of U2 is directly the same idea as U1 or U0. It is, U2 is how far off your quadratic slope is from the average one. So it's individual differences in the extent to which improvement is slowing down over time. Some people may level off faster than others. Some people may continue on a gradual decline. So now we've allowed individual differences in each parameter that's characterizing this trajectory: the intercept, the effective linear time, and the effective quadratic time. How the model predicts a expected outcome at any occasion or an expected linear time slope at any occasion is exactly the same because there's using the fixed effects only. So none of that changes. The one thing that will change relative to the previous model is the denominator degrees of freedom with which the fixed quadratic slope is tested. It's going to be closer to what would be level 2 persons rather than level 1 occasions. So in the code then, if I'm using SAS, I've got my quadratic time on the random line here. If I'm using Stata, it yelled at me when I tried to do an interaction term on the random side. So I made up a new variable that I called time SQ for time squared. I have a rule in fighting with code. If I know how to do something and I can't make it work in a simpler way in 10 minutes, I just do it the way I know how. So time squared is the same thing as time multiplied by time. It's just that Stata yelled at me when I tried to do it that way. In R, it looks like it did not yell at me. So now I have time squared inside the parentheses to the Elmer call so that it has its own random effect. So question then, if I add a random quadratic time slope variance to the model, so I'm allowing each person their own U2, I'm estimating the variance across people in those U2 random quadratic slopes, how many total parameters am I adding? And don't say one. Because when we added random linear, we also added a covariance with the intercept. So if we follow that same practice, then how many am I adding this time? Got one vote for 3.
Is it 4?
It is actually 3 in this case.
It is 3, okay.
It is, because the 4th would be a covariance with the level 1 residual, and that is not allowed. So the covariances among random effects are only the random effects at that level. And I have a shortcut that you can use to figure this out. So in the part of the model code that specifies random effects, the change in the model degrees of freedom from adding something new is equal to the number of terms that are random. So let me say this differently. Oh, come back here. Hang on. Oh, sorry. It just jumped to a whole nother thing. This is what happens when I have like a 10-foot monitor in front of my head. I can't see very well. Where are we? Fixed linear time. Okay. Just close your eyes if you're seasick from scrolling. Okay. Here I am. So if I don't have these in here, if I just add a random intercept, that's degrees of freedom 1. If we add in a linear time slope, there's 2 things on the line, that's degrees of freedom 2. If we add in the quadratic, now there's 3 things on the line, that's degrees of freedom 3. 3. I sound like my son. It's free. 1, 2, free. Get it? 3. If I had a cubic term, then how many total parameters would I be adding if I did something crazy like this?
6?
So there would be 4 new ones in that
Okay.
case. Yeah, so what you were saying before. In this case, it would be a 4x4 G matrix, which would have 4 variances and 6 covariances in it in that case. But I'm not going to do that kind of craziness. So generally speaking, you can figure out how many parameters you've added to your model every time you add a random slope, because you have its variance plus the covariance with the random effects that were already there at that same level. So what we're saying is that where people start gets to be related to how quickly they change at first, gets to be related to how quickly they level off. All of those terms characterize the data for one person, so it is reasonable to have covariances between them. Not just reasonable, but most methodologists would say, yes, you need them. Otherwise, you're likely to have misspecification. So then that means we'll do likelihood ratio tests to see whether or not those 3 terms help. Okay, so our R matrix at level 1 looks the same, but it has less variability in it, because part of what we were saying is E-variance, why are you off your line today, is, well, I'm off my line because you made everybody have the same bendiness, and after giving each person their own version of bendy, the E's have less variability. The line fits better to each person's individual data. So part of what we were calling level 1 within person across time variance is now attributable due to person differences in quadratic at level 2. So this model then has 4 kinds of variability in it. It is a 4-pile model. We have E-variance at level 1, and then at level 2, we have between person differences in intercept, linear slope, and quadratic time slope. So in the G matrix, 1, 1 is our intercept variance, that's at time 0. 2, 2 is the linear time slope variance, and this is now also at time 0 because of the random quadratic. So 25, 8, 40, that number there, that represents between person variance in the linear slope at time 0 specifically. Individual differences in initial rate of change in this task. And then the 634 here is individual differences in the quadratic time slopes. So each person's deviation from the fixed slope, that's the variance across people of those deviations. Then we have the 2 covariances that show up along with it. And you'll note in the G-core matrix, so this is where we have correlations rather than covariances, this, an almost perfect negative correlation. Because do you think that the effect of time and time squared would be related? Yeah, probably. So this is something potentially to watch out for. You can reduce the correlation between the linear and quadratic slope to some extent by choosing a different time 0 that's near the middle, but that may not be as useful to you as a time 0 that's at the beginning or the end. So just a heads up that when you're dealing with these polynomial models, there is going to be collinearity between time and time squared, and that can potentially cause estimation problems. So here's my V matrix. This is what the model now says the variance and covariance should look like over time in total, marginally. And where that matrix comes from is given by these 2 equations here. This really ugly thing, so that's how we get the predicted variance at each occasion. And note the end of it here, t to the 4th. So this is a changing pattern of variance over time that follows, I think you allowed me to make up a word, a quartic pattern, time to the 4th. If time to the 2nd is quadratic, I'm calling this quartic, as well as all of the other terms related to the variances and covariances. So it's a fairly complex function, but it is still a function. Likewise, the predicted covariance between any 2 occasions starts with the random intercept variance, and then it depends on which 2 occasions you're talking about. So this is still heterogeneity of variance and covariance over time, but of a different flavor.
Lisa, I wanted to ask, what would you do in the case that, let's say that half of the sample follows like that predicted variance, and then the other half has a linear, like a completely different relationship? Is that a piecewise model, or how would you approach that?
I think that to the extent that for a large chunk of the sample that a linear slope is sufficient, that would show up as having less power to detect the random quadratic slope, because another way of thinking about it is that they would have a slope deviation that is, if the fixed quadratic were sufficient, then they'd have no slope deviation. If they really were, they didn't have a quadratic at all, then that would have to show up as counteracting what the fixed quadratic is doing, and it would still limit the variability either way.
Okay, so there's no way to, like, in the same model, have some people following a linear relationship, with time, the other half, something like a polynomial or quadratic.
There is a way if you know who those people are.
Okay.
So like if you had a hypothesis that, say, the control group should follow a linear treatment trajectory, whereas the experimental group should follow a quadratic trajectory, you could set that up. It would require essentially indicator variables in the random effects that would turn on the random slopes for certain people and off for others.
Okay.
So yeah, I think you could do that. Now, if you're talking about trying to figure out like latent classes of people who follow different patterns, that's heading into the genre of what's called growth mixture models. And I have the same problem with those models as I have with exploratory factor analysis, in that you can come up with latent classes for any reason, lots of reasons besides the one that you're hoping for.
Okay.
Those models are super sensitive to violations of assumptions, by the way.
Yeah, because I'm thinking like if you have a group of students and some of them maybe are gifted and they like rapidly learn something, and then the other half are just learn it at like a linear, slow pace. If that can be modeled in the same model, or if it requires two separate models potentially.
I think it could, but I don't know that quadratic would be as useful as something that includes a direct asymptote.
Okay.
So the problem with these models is the U is either going to flip over and come back down or start going back up again. And that's an unreasonable thing from a theoretical point of view.
And if, just as an example of like a cubic relationship, would that be like if somebody improved, decreased, and then started improving again?
Yes.
Okay.
Yep. Yeah, so if it started to level off, but then they took off again, that would be a cubic. And I do have a paper where there's a cubic model in it, and that was exactly what happened. It was like growth of reading that all of a sudden accelerated after second grade, when other skills were coming online was sort of the rationale, I think.
Okay, thank you.
Thank you. All right, big ugly equation. Take-home message though, heterogeneity. That's your take-home. So in the same way that we had alternative covariant structures that had different patterns, right? We had, compound symmetry where everything's supposed to be the same, or AR1 where everything is, a function of some parameter, squared, cubed, etc. We had topolets, we had all these different patterns that we could choose from. This is another pattern. So it's a different prediction than what random linear alone would say the pattern is. This adds these extra pieces to what the function would look like, and its variance is a function of time to the fourth power. How do I know if we need all this? So I had to add 3 things to make this model go. How do I know if they help?
LRT.
Yes. Any question about something about variance, it's a likelihood ratio test. Yep. So we did that. Difference in -2 log likelihood on 3 degrees of freedom is 38. P-value is 0 to 8 decimal places, so yeah, we'll say that's good. So how do we know? Likelihood ratio test right above. Do I need to compute pseudo R-square for this model? I would say no. Other reasonable people might disagree with me, but I say no. Because I don't think it makes sense to talk about random effect size in terms of an R-square. What we have done is take what used to be error at level 1 and reallocate part of it to be a different kind of error at level 2, error that is a function of acceleration or deceleration of individual trajectories. But because we still don't know why each person needs their own quadratic, to me it's still error, and talking about it as explained variance is just not cool. That's my perspective. So what you might do instead, here's some confidence intervals that describe the extent of variation. So the differences that are predicted at time 0, the differences in linear slope at time 0 that are predicted, and the differences in quadratic slopes that are predicted as well. And I have a note here, these last 2 confidence intervals overlap 0. Is that a problem? It is not a problem because these are not your typical confidence intervals. So the fact that they overlap 0 means some people don't have expected change. They might be heading up instead of down, or it's 0 would mean no change. So the fixed effects that are in the middle of these intervals are tested for significance against 0, and they're already significant, which is why it makes sense to continue and talk about change in this way. Okay. So we have then one more model along these lines, taking apart the R matrix. So based on the original data that I'm modeling and the fit of how well the fixed trajectory is characterizing the means and how well the combination of random effect variances and covariances is characterizing variance over time, I don't think it makes sense to try cubic. So I'm not sure if this is good enough yet. One thing that I can try, though, is to change the R matrix. So these models up to this point have assumed that the only reason for the covariance between occasions from the same person is because of random effects, is because of individual differences in intercepts and slopes, and that once we take those out and put them over in G, what's left in R can have no covariance across the residuals. We can test that assumption. So we did this in example 5 as well. For instance, I'm going to test that assumption by adding an AR1 correlation to the R matrix. So this is asking the question, after controlling for individual differences in intercepts, linear slopes, quadratic slopes, are the residuals correlated at all, basically, in this type of pattern? We're assuming they haven't been. Let's check that assumption. So I can do AR1 as a direct structure within ProcMix. I can do AR1 as a direct structure using the residuals command in state as mixed. But in R, I had to switch back from LMER to just regular LME, which is in a different package. So that's why the code looks different, is because it is a different package. On your homework, I will tell you what to use so that you don't have to figure that out. I will have already figured out at least that much. So here we have the fixed part of the model. The random part of the model is given as a separate argument. And then we also have this correlation argument that allows us to add in the AR1 correlation amongst the residuals. So I then asked for all of the matrices that build the model so that we could look at those. In order to do a likelihood ratio test using the ANOVA package, I had to re-estimate the random quadratic model using LME as well. So I found that I couldn't essentially compare results across packages because LME uses ANOVA, LMER uses RANOVA, and I couldn't make them work together. So I re-estimated the model so that it would be within package so that I could do the likelihood ratio test to see if the autoregressive helped. So here's the R matrix that I end up with, and the new component is right there, the 0.17. So that is the estimated correlation among residuals that are 1 session in time apart. 0.17 squared gives us the expected correlation of residuals 2 sessions in time apart. 0.17 to the third power gives us 3 occasions apart, lag 3, and so on. I've got my new autoregressive correlation. According to the Wald test for it, says it's not significant. I can do a likelihood ratio test just to double check that, and it looks like this. I would come to the same conclusion. Adding that one autoregressive correlation in the R matrix for the residuals doesn't help anything, so it looks like the residuals being independent is a reasonable thing. So here's some pictures then. First picture then is showing the differences in the models that we looked at with respect to their prediction of the means across time. So saturated means is the right answer. That's given by the black squares, so they're a little bit bumpy. Empty means, as the other baseline, is given by the flat line right here. Random linear is given by the straight line, and quadratic is given by the line with the diamonds on it. So if we just look up to session 6, which is where we stopped collecting data, what do you think of our quadratic model? This is an opinion question. We'll do a little visual analysis. What do you think?
It looks like it fits better, but can we assume that it's going to curve back up after session 6?
We can assume that because that's what the model says.
Okay.
So do I know if quadratic is better than linear with respect to capturing the means? Do I know that yet or no?
Visually, I mean, it looks like it's closer.
It does.
So I'm gonna say we do know this.
We do know that if we stare at it. We also know it because we tested whether a fixed quadratic slope adds anything beyond the fixed linear time slope. So we do know that quadratic fits better than linear. Do we know if quadratic is good enough?
Not by looking at it.
Not by looking at it. So that's where we're headed on Thursday. But yeah, if we follow past session 6, what these models say would happen. The linear model says, yep, they're just going to keep improving forever. And the quadratic model says they're going to flip and come back up the other side.
I wanted to ask though, how do we know that it's quadratic and not hyperbolic? Like that it's just not hitting a floor and is gonna just keep constant hovering
We,
around that floor.
we don't know what the right answer is in these data because they're real data. But what we have is a prediction from a quadratic model, and I'm setting up is the idea of, are we there yet? Like
Okay.
like we can build and say each new thing has helped so far, but how do we know if it's good enough or if whether we still need things? And
Okay.
if it's not good enough, then we might need to consider a different functional form, such as hyperbolic or some other kind of truly nonlinear model that has an asymptote. Because yeah, this, I think, theoretically, both of these options are problems. People don't keep improving forever and ever, and hopefully they don't start getting worse and eventually go back to where they were. At least not in this context. Yeah.
Could we choose a hyperbolic relationship for change? Like, would it follow the same process as this, but we just would use a hyperbolic thing instead of a quadratic thing?
Unless you can find a way to linearize the hyperbolic, then you would have to be in a different estimation approach for nonlinear models.
Oh, I see.
Yeah,
I
so
see.
this is slope times variable plus slope times variable, which is why we can fit it using any of these packages. If there's like an exponent or stuff like that in the model, then you can't throw that into mixed or Elmer.
Because if you take the derivative of a hyperbolic function, then you get natural log, and that gets all crazy.
Yeah, you can't use the same software. I'm not going to say it can't be done, but it's trickier.
Okay, that
Yeah.
makes sense.
Yeah, and so then we do the same thing on the variance side in the second picture here, and note the craziness of what is expected to happen. So the linear model predicts changing variance that's quadratic, that's the triangles here. The random quadratic model predicts changing variance that's quartic, and that's why that's just going through the roof here after session 6. So we can ask the same question, given the saturated unstructured model results, are these good enough yet? We don't know the answer, but that's where I'm headed next. So we will stay tuned for the exciting conclusion of, is this model good enough? Spoiler alert, the answer is no on Thursday, which will motivate us to try a few other choices. All right, 1:45, that means it's over for today. Any quick questions before we call it a day? All right, then we will be back on Zoom on Thursday. After that, I will let you know as soon as we get updates on our classroom. Thanks for being here. Office hours tomorrow if anybody wants to chat with me.